All right, cool. Thank you very much, Daniel, for the introduction. And also thank you everyone for coming to this presentation. I'm super excited to talk about this work, AppWorld, reliable evaluation of interactive agents in a world of apps and people. This is joint work with many of my amazing collaborators from Stony Brook University, Allen Institute for AI, and Saarland University. I've prepared this talk to be around 40 minutes. I think there should be enough time for discussion. So feel free to ask questions anytime during the talk. All right. So I want to start this talk by painting a broad vision behind this project before diving into the specific work. Many of us already use AI agents that act on our behalf in the digital world. For example, assistants like Siri, Alexa, and Google Assistant are agents that can already do simple tasks on our behalf, like setting an alarm, checking weather, and making a call. In the future, I believe these agents will become far more capable. They will be used for doing more complex tasks and will be adopted and integrated even more broadly into our society. Everyone will have their own personalized AI agent through which they will interface with the digital world and to some extent, even the physical world. These agents will coordinate with each others and even with humans to achieve complex collaborative tasks. There will also be agents that act on behalf of organizations like hospitals, banks, and so on. And their actions will deal with real world resources that will have real world consequences like transferring money, sending medical records, and so on. So, as we move towards such a world, it is important to ensure that these agents become more capable, reliable, and trustworthy. Our long-term goal of this project is to build a simulated world which acts as a foundation for reliable evaluation of such agents embedded into our society. AppWorld is a step towards this long-term goal. And that is what I will talk about next. AppWorld is a simulated world and a benchmark that focuses on this setting where AI agents individually and autonomously complete day-to-day tasks on behalf of people on their app accounts. It includes tasks such as returning an Amazon order and buying a replacement, sending owed money to friends on Venmo, and canceling meeting reminders based on coworkers' emails. Agents can operate apps to do such tasks broadly in two ways: by interacting with the browser and mobile user interface, or by calling APIs exposed by these apps. At the end of this talk, I'll briefly discuss our ongoing work on agents interacting with the user interface. But for most of this talk, I'll focus on agents calling APIs. Although calling such APIs is the main ingredient, just that is not enough for complex tasks. Here, the calls to the APIs have to be made by writing rich code in an interactive manner. Let me explain it by showing how an ideal agent could tackle an example task, that is, play my shortest Spotify playlist with enough songs for today's workout. My workout plan is in simple note. To solve this task, first, the agent has to find the user's workout duration. For this, it gets the user's simple note credentials, logs in, searches for the workout related notes, all via writing a code snippet, making appropriate API calls to the simple note app. Notice here that the output of the first API is going as an input to the second API. Still, both of these calls can be made into the same code snippet, even without knowing the value of the token variable. This is possible if the agent knows the output schema or type information of the first API and the input schema or type information of the second API. However, what to do next depends on the free-form text present in the notes variable, and so the agent has to print it. The agent finds a note with free-form text indicating day-wise workout durations, so it prints the current day to find today's duration. Notice here that the agent printed today's day because it found a note with day-wise workouts. However, the user's notes could have been organized in many different ways, each of which would have required a different code snippet. For example, if there was a note with month-wise workouts, the agent would have printed the current month instead. This means that the second code snippet here had to be written interactively based on the first code snippet's output. All right, so now the agent knows today is Tuesday. So it infers a 45-minute workout and searches for a playlist with enough songs for that duration. To do this, agent has to loop over the playlists, find total duration for each, and filter and select them accordingly. Doing this involves writing rich code with various programming constructs like loops, conditionals, arithmetic, and so on. In summary, we saw that a seemingly simple day-to-day task can be quite complex, and it had two key requirements. It required environment interaction to write the next code snippet, and the code itself was rich with various programming constructs. So the key question we ask in this work is, how can we develop and benchmark such rich and interactive coding agents for complex digital tasks in a rigorous and reproducible manner? To do this, as it will become clear later, we need three ingredients: a realistic and reproducible environment of API operable apps for agents to interact with, a benchmark of complex tasks requiring API calls with rich and interactive coding, and a robust programmatic evaluation framework for checking agents' goal completion. Now, there are many existing tool use benchmarks like Gorilla, Toolbench, API Bank, and many more, but they do not support these requirements. Their tasks are simple with only a linear sequence of 1 to 4 API calls. They have small number of API implementations or use unstable APIs. And they use human or language model-based judgment or reference-based evaluation, which is not robust for complex tasks that have many solutions.
Can I
Yeah,
up here, going back to the previous slide?
yeah.
When you talk about a linear sequence, I suppose you're um, contrasting it to a nonlinear sequence where you might not realize whether I should go this route or that route. Like there's some sort of branching element in your decision making. Is that right? Is that a right interpretation?
No, I'm contrasting it with this rich coding requirement that I discussed before. So I'm contrasting it with the thing on the right.
Uh,
So
uh,
there is like a rich
oh,
code with various programming constructs like
I
loops, conditionals, arithmetic, and so on. So it's not just three three API calls, 1, 2, and 3. That's pretty much it. So
That's fair. So basically, you're saying that sometimes when I do API calls, it's not just going to return me a single value, but perhaps it's a complex structure, perhaps it's a hash map in which I might need to do some Python coding and some Python manipulation.
yes, yes.
Got it, got it.
And I'm also contrasting it with just the number of APIs and the complexity of it. It's like 1 to 4 versus 5 to 25. And also the nature. So it's just not API calls, because as I will show later, it might require even like more than 100 API calls. So when you have like constructs like loops, conditionals, and all of these things, it can help you, make that complex thing that has to be done much simpler and manageable.
Got it. Thank you.
All right, cool. That's a great question. Uh, all right, so here we discussed what the shortcomings of the previous works are.
Can
And
I can I ask one more question?
yeah.
Now that we've already stopped. So the last box is about a reference-based evaluation.
Mhm.
Um, Actually, can you expand more on that? So, like, even here, I suppose you have to have some sort of reference. Is emphasis in the last box about whether you have some sort of ground truth goal data or not, or whether it's about whether they support interactive exploration of the world or not?
Yeah, I'll talk a lot more about evaluation in the evaluation section, but very briefly, we do not care about the path at all. It's all about the state, whether you achieved the goal or not, and you can determine that just based on looking at the state of the environment, which in this case is the database state behind these apps.
Got
Uh,
it. Got
yeah.
it.
So it's
Some,
not, we don't care about, like, you could
yeah.
write code in like any language and you could make any API calls, whatever. We don't care about that at all. And whenever you have like complex tasks that can be solved in many ways, and even when you have like hundreds of lines of code, there's just so many ways of doing it. It's just impractical to do reference-based evaluation, like comparing it somehow with the cold solution. So it's more state-based and unit test-based evaluation. I think it will make more sense when I come to that section.
Thank you.
Yeah, cool. All right, so we discussed the shortcomings, and now to bridge this gap, we introduce AppWorld, a world of apps and people, which constitutes a new environment, a challenging benchmark, and a robust evaluation framework. So I'll talk about these three components, starting with the environment. So we want to create an environment of API operable apps like Amazon, Gmail, Venmo, and so on. We want this environment to also support reproducible experiments, complex tasks, and robust evaluation. Reproducible experiments require resetting the start environment to identical state whenever we want to run an agent on a task. Complex tasks require tailoring the start environment specifically for that task to be compatible and challenging. And lastly, robust evaluation requires accessing the final environment state, as complex tasks can be solved in many ways. So to satisfy these requirements, we need full control on the state of the environment, which for an app-based environment is defined by the databases underlying each of these apps. So in other words, we need full control on the app databases. This rules out the option to build this environment from real apps implemented by companies because their proprietary app databases are fully controllable only by them and not by us. So instead, we implement simulated versions of these apps in our own backend of APIs and databases, which provides us or anyone with full control on app databases. Simulated apps also provide other benefits over real apps. The real apps require real resources. For example, a Venmo payment needs real money, whereas in our simulated apps, it is just database entry indicating who paid whom what. Simulated apps are also fast, always up, and have no rate limits, which is not the case for real apps. But all of these benefits of simulated apps are not enough. We also need richness, realism, and complexity of the real apps. And to do this, you have spent huge amount of effort in this work, making these apps to be super rich and high fidelity in nature, meaning that they have closely similar features and behavior to real apps. Our implementation spans over 60,000 lines of code, have 457 APIs with detailed documentation and 100 plus database tables. Our apps have fine-grained and detailed functionalities. For example, the Gmail app won't be just send and read emails. As it is in real life, emails will be organized in threads within your inbox and outbox. You can reply and forward individual emails from them to different contexts. You can schedule them for a future time. The threads could also have your drafts. You could attach to and download files from them. You can mark them read, spam, archive, organize them by labels. And you could also do advanced and full text search with various criteria. And this is still a small list of things you could do in the simulated Gmail app. Actions or API calls in our apps also lead to realistic in-app and cross-app consequences. For example, when you place an Amazon order, your cart is cleared, the product inventory is updated, your payment card is debited, the order shows up in your past orders with the tracking information, and you get an email confirmation with a receipt as an attachment. These apps also have authentication and privacy features like login, sign up, forget and reset passwords, and so on. And they also prevent access to others' private information. These APIs always provide informative error messages and never blanket errors like an internal server error. For example, if the agent tries to send money to someone via a payment card that does not have enough balance, the API will respond with a message saying so. This allows the agent to learn via interaction. And finally, these APIs have documentation with detailed input and output schemas as well. These apps also have been extremely rigorously unit tested. We have over 1700 plus unit tests spanning 34,000 lines of code and providing a test code coverage of 98%. We want the agents to be able to explore this environment arbitrarily without the environment breaking or behaving unexpectedly. This rigorous testing gives us high degree of confidence that we have such a reliable environment.
Excuse me, Hash, can you be more like specific about like the input output of the like APIs?
Yeah, so essentially what I mean is that imagine these APIs are like Python functions. We would have detailed documentation of what arguments they have, what type they are of, a description of them, and that gives you an input schema. And we also provide an output schema, which is basically what JSON structure they would output, like what are the individual fields. If the individual fields are like, again, like nested dictionary, what structure they would have, if it's a list, if it's a list of what, and so on. Does that
Okay,
make sense?
like for example, like the show product API, I can see like there's some, I guess like potential values for like name should be a string, description should be a string, but like is there anything like more detailed about like, say for example, the product should be particular categories or like the name should like have some like more detailed, I guess, like requirements.
So there is an explain. So there are two things that we have. It's like a constraint, like if it's an integer, if it's, let's say, rating, the integer could be only like 1, 2, 3, or 5. So there would be constraints like that. There would also be descriptions of what individual fields are, and there would also be overall description of the API itself, like what this API does, how it behaves, and so on. Does that answer your question?
Yeah, I think it is.
Yeah, so this is very small. So the documentation is like very detailed, and you can also go online and look it up on appworld.dev. This is just like a very small snapshot just to convey something about it.
Okay.
All right, so coming back, we discussed these two properties. And yeah, and as discussed before, these apps also provide full programmatic control over the database state. And we use this control to populate app databases with rich and realistic data. As I will show later, this data will help us build complex tasks. In particular, we create a simulated world of 100 plus people. In this world, each person has their own personal accounts on all apps. They have a home and work address for online delivery and payment cards for monetary transactions. This allows personal tasks like buy a t-shirt for my home delivery using my Visa card. These people are also related to each others in the world via various relationships like parent, friend, sibling, and so on. And this allows for relational tasks like email my partner that I'm running late. These apps are also populated with personal and interpersonal digital activities of people which are consistent with their relationships. For example, on the top, you see an employee sending an email to his manager asking for a leave approval. And on the left, you see two roommates chatting about the apartment bill payment over the phone, and so on. These activities are populated spanning 2+ years of time, which allows for temporal tasks like delete my emails from last year. Overall, the resulting database has 100 plus tables, 350K plus rows, and 750 plus columns. This simulated world of apps and people, which we call base world, provides us with a rich and realistic foundation to build complex tasks on top of. And as I will show later, uh, uh, this will help us build complex tasks, as I will show later in the benchmark section. All right, so next I'll talk about the benchmark and specifically how we design complex tasks. So we start by writing day-to-day scenarios, which naturally require rich and interactive coding. Here, a scenario is an ungrounded blueprint for the task. For example, buy the product that my related person suggested someday. From this scenario, we can create multiple tasks like buy the shirt that my roommate suggested today, buy the desk that my coworker suggested yesterday, and so on. Remember that we want agents to follow this instruction by taking actions in the environment. So just the instruction is not enough to define a task. We also need a world state, which constitutes the database state and current time within the world. And we also need a supervisor, who is the person in the world on whose behalf the agent is supposed to operate the apps. For the task to be solvable, we need the instruction, world state, and the supervisor to be compatible with each other's, meaning all conditions required to follow the instruction are satisfied in the world state for the supervisor. For example, in this task, today is 11th of February and the supervisor is Alice. Here, as per the database, Alice's roommate has suggested her to buy a Nike shirt today via a phone conversation. This Nike shirt is available now on Amazon, and Alice has enough funds in at least one of her payment cards to make the purchase. These conditions make the task solvable. However, mere solvability is not enough. We also want tasks to require thorough reasoning to solve. For this, we include distractors, hurdles, and task variations. Here, including distractors means making it so that bypassing any reasoning step will likely mislead the agent to the wrong path. For example, here Alice will have shirt suggestions not only from today, but also from days before. So if the agent ignores the word today, it will likely fail to identify the correct shirt to order. And similarly, there will also be other distractors as well. So if the agent ignores the word shirt or roommate, it will also similarly get distracted. Next, we also include hurdles, which require agents to do realistic failure handling and adaptation. For example, here, one of Alice's payment cards has no money in it. So the agent has to realize to try another card when it fails. And lastly, we also include task variations, which requires agents to reliably solve tasks under slightly different or contrastive conditions. For example, remember that we created this task by grounding this scenario. Similarly, we can create a different task by differently grounding the same scenario. Notice that the two tasks have different current times in the supervisor. They have different placeholder values. And they have different but appropriate database state to satisfy the previously discussed task properties. These task variations also help us catch shortcuts that distractors cannot. For example, here, the agent was supposed to check for suggestions in both phone messages and emails, which are the two modes of communication in AppWorld. On the left, the key relevant suggestion has come via a phone message, and on the right, it has come via an email. So if the agent checks only the phone, it can find the correct item to buy on the left, but not on the right, and vice versa. All right, so now that we know what we want from these tasks, let's see how to ground the scenarios into tasks so that they satisfy the required conditions. To do this, we use the base world that we discussed earlier. Remember that this world already has a rich, fully populated app databases, including people and their activities. This world provides a reusable foundation that can be used across scenarios. However, it does not satisfy task-specific requirements. So we will need to adapt the base world for each task, as I will show in a bit.
I have a question here.
Yeah.
For the base word, I might have missed it, but can you remind me like how the base words database is collected? It's like fully human, like basically they're simulated people, but it's actually a real human annotator acting behind them, like as if they're using the app by themselves. Where they are also collected somewhat automatically, like those simulated people are also like kind of powered by LLMs.
Yeah, so that's a great question, and I think I should have clarified that, but that's okay. Okay, so let me just go back to that slide. I can explain that better. So that's not the case. So the data here is so there is an asterisk over here. So data is not popular, is it's kind of procedurally generated, and the people here are not simulated by a language agent itself. So the way we do this, I think if I give like one example, it will probably make more sense. For example, we have over 100 tables with different relationships and so on. So here I'm just giving you an idea of how a Gmail emails related table could be populated. So the way we would do it is that we would write like many different templates about conversations that different people can have with each others, like what kind of email threads two roommates could have with each others, or multiple coworkers could have with each others, or a parent and a son could have with each others, and so on. So we have this huge number of templates, and then we instantiate those templates with different people across a span of 2 years of time. And that is done procedurally by sampling and so on. But the templates over here are they are it's a mix of both like human and chat GPT. So we write some templates and we maybe use chat GPT to give us some more ideas, but in the end all of that is like we read all of the things that chat GPT generated, and then we use that to sample. So that gives you an idea of like how this one thing is done. Now it is a quite more complex like procedure because it's there's a lot involved, a lot of relationships, dependencies, and so on.
Thank you. And like two like short follow-up question to that is like first, how you ground. I mean, this might go into a little bit too details if like so you can skip it. Like, I'm just curious, like how you ground these like human or ChatGPT generated template to actual like API calls and ensure their accuracy. Like basically, you have a template saying like these are relation between like the boss and the worker, and they have this kind of communication. How can you make sure that if one to generate the base word like activity or data, they can be exactly ground to like the same the accurate piece of email that they really communicate based on your template?
Yeah, that's a great question. So essentially how we do it. So I think one thing I should point out is that there is because there's a lot of complexity in the database, we cannot write like SQL queries because, as you said, there's like a lot of dependencies, and if you like place in order, a lot of things would happen. So if you are just like writing this SQL operations, it would just be an absolute nightmare to do this kind of elastic population. So what we do is, again, we go back to the APIs that we have developed, and we are sure that they are working appropriately because we have just tested the hell out of them. So for example, let's say I take this example on the top. If I want to make this this employee send an email to his manager saying, can you approve my leave for tomorrow? I would explicitly first make an API call programmatically to log in that first, like this employee via his email and password. So I get the access token, and then I would make an API call to Gmail email API with the appropriate content. And then we have this control that you can make API calls or simulate the behavior of making API calls at any point in time. So I could say it would happen like 2 years back or 1 year back or whatever. So we basically use this APIs as like an atomic operation to basically populate the entire database. And we do make API calls on behalf of these people, just programmatically. Does that make sense?
Yeah, that makes super sense. Thanks. And I'm afraid I'm taking too much time, but the last thing is like it will be. I'm not sure if it's beyond the scope, but it will be interesting to have analysis of the distribution of these templates activities and how they like align with like more realistic scenarios when like people are using real apps. Like are they typically doing this type of thing where they follow a certain pattern of using these APIs or sort of thing. But yeah, that might be kind of the next step. I don't know.
Yeah, I think that's a very good point. I think I should also mention that you could definitely do like agent-based population, as you pointed out, because the way we are making this populating is explicitly, is essentially via like making API calls on behalf of people. So you just have to like replace that with like an language model, and you could do that. The reason we do not do that is that we in the task construction, we have to make sure that the data that is going on inside our database ensures that the task is solvable. So if you just let language models generate anything, it could generate data that could conflict with the task. So that's why we do not do it. But I think your point is valid and something we should consider.
Got it. Thank you so much.
One more question that we have stopped. Is the whole world for us just APIs? Is there at any point do we interact with like any graphical interface, or it's just API calls?
I'm sorry, I missed the last part. API calls are what?
So you're simulating, for example, Venmo. Do I ever interact with the graphical interface of Venmo, or is it's always about API calls?
In this work, it's about API calls, but in the future work, I'll talk later, is that we have created a UI for basically all of these apps. So like it would look like real Spotify, real Amazon, and they would interact, or they would, like when you click a button to play a playlist, it would, in the backend, it would make an API call to our backend, and everything else would be the same. But that's not this work. That's like a follow-up work.
Thank you.
Cool. Thanks. All right, so here what I was saying was that we have created, we want to instantiate these tasks via from scenarios and the base world that we created or we discussed earlier. And this base world provides us like a reusable foundation that can be used across scenarios. However, it does not satisfy some task-specific requirements. So we'll need to figure out how to adapt the base world for each task, as I will show in a bit. So to ground the scenarios, we need to do two things. We need to select the placeholder values like shirt for a product, and we need to satisfy the required conditions. Some of these conditions can be satisfied by doing a search in the app databases of the base world. For example, to find a compatible supervisor, we can find a person in the world who has roommates. However, for other conditions, search is not enough. Instead, we need to edit the app databases. For example, the base world does not have phone conversation about the shirt suggestion between Alice and her roommate. So we need to create a conversation, which we do by editing the app database. So note that this is a simplified picture. In practice, there are many conditions, often interdependent with each other's. So for flexibility, we do all of this programmatically by writing the task setup code for each and every scenario. And now that we have the tasks, we also want to programmatically guarantee that they are indeed solvable. And for this, for each task, we write the solution code and evaluation tests. And then we programmatically verify that running this solution passes all evaluation tests. Here, I want to emphasize that each task scenario poses unique requirements. So all code has to be written individually for every scenario. It has taken us over 5 hours of time for each scenario, over 40,000 lines of code. And to maintain high quality, all scenarios and code have been developed by us. It's not crowdsourced, and they've also been reviewed multiple times by multiple people. And here are some more example tasks from AppWorld. I'll go over the first two of them. The first task is the agent has to find, the first task is I'm going on a camping trip with my siblings. I emailed them a checklist of the needed items, check who committed to bring what, then order the remaining items on Amazon. The second task is I booked a few hotel rooms today for my upcoming trip. How much did I spend in total from my Visa card based on the email confirmations? And so on. All right, so to solve these tasks, the agent is given an instruction, the API docs to understand how to use the APIs, and an interactive coding shell with an API client to call app APIs. By default, we provide an IPython-based shell, but one can really use any programming language with an HTTP client of their choice. Via this shell, agents have access to all day-to-day apps and also to helper apps. The API Explorer app, which has APIs to explore, search and explore API docs interactively, and the Supervisor app, which has APIs to get supervisors' personal details like app credentials, payment card information, and so on. Based on our written solutions, we find that AppWorld tasks are quite challenging. They require 1 to 4 apps, 5 to 25 unique APIs, and 10 to 200 API calls and 20 to 130 lines of code. All of this is assuming perfect knowledge of APIs. In practice, agents require many more API calls and lines of code as they learn by interaction and exploration. We have 750 such tasks built from 250 scenarios. From these, we hold out 2 apps, Amazon and Gmail. All tasks involving any of the 2 held out apps are moved into the test challenge split. And the remaining are randomly divided in the train, dev, and test normal splits.
Question?
Yeah.
So you had an example where you had a template with variables in it where you were like replacing in conditions. When we say task, are we referring to the templates or the instantiations of the templates?
Yeah, so the scenario is what we are calling this, you could say the templates. So that's, and the tasks are instantiations of them. However, it's not just, I should mention, it's not just replacing values. There are also like a lot more going on in making sure, that is contrastive in nature. The environment also changes accordingly. There are other changes also happen that that I discussed over here.
Got it. So is a scenario more like a collection of templates?
No, scenario is a collection of tasks, in particular 3 tasks.
Okay, I'll need more thinking to do on that. Thank you.
Yeah. So over here, you see on the top, you see a scenario, which you could think of as like a template. And bottom, there are like 2 tasks. In practice, we create 3 tasks for each scenario.
Thanks.
Okay. All right. So we have 2 test sets, test normal and test challenge. And from this, test challenge is our main test set. Because it forces learning to use APIs for held out apps by reading and understanding the API docs. And a test challenge also has inherently harder tasks. All right, so next I'll talk about the evaluation. So now that we have tasks, we need a way to robustly and programmatically evaluate agents. Agents can solve such tasks in many ways. For example, they can download Amazon receipt from its API or its email confirmation. Both are perfectly valid. So comparison to a reference solution cannot be used. Therefore, AppWorld uses a state and execution-based approach. In particular, the agents start with the initial state associated with the task. The agent makes a series of code executions, many of which may be state changing, and we get the final database state. We compute the difference between these database states to obtain cumulative changes that the agent has made to the tables, rows, and columns. And then we programmatically check whether they include all desired and no undesired changes. We do these checks roughly in a hierarchical fashion, going from tables to rows to columns. For example, for our task about buying a shirt on Amazon, we first check that only a small list of tables has changed, namely Amazon orders, inventory, and so on. And the simple assertion captures vastly many ways an agent could cause undesired changes or collateral damages. For example, if the agent initiates an Amazon order return when it was asked to buy something, Amazon returns table will change and this test will fail. And we then check only one new row has been added to the orders table, and then this order only has the expected Nike shirt and nothing else. So the key effect of doing this is that regardless of what path the agent takes to make the desired changes, for example, using Visa card or MasterCard, as long as it adheres to the instruction, it will pass. And similarly, regardless of what undesired change agent makes, for example, returning an Amazon order when deleting emails, it will fail. Excuse me. For example, returning an order or deleting emails, it will fail. All right, so using these assertions, we define two evaluation metrics: task goal completion, which checks that all tests in a task pass, and scenario goal completion, which checks that all tests for all three tasks in a scenario pass. All right, so next I'll discuss the experiments. So we benchmark agents built from open and closed LLMs with many strong few-shot prompting methods for interactive decision-making and coding tasks. I'll very briefly discuss the prompting methods. The first one is React. React agent, as you already know, it generates a natural language thought about what it wants to do and follows it up with a code snippet to do that. The environment provides an output or error stack trace depending on whether the core execution succeeded or not, based on which the agent decides what to do next and the sequence continues. Because our React trajectories are long, we also have this planning-based approach, which generates a high-level plan and then executes each step of the plan via a React module. Because at the core, our tasks require making API or function calls, we also test native function calling abilities of language model, for which they are explicitly pre-trained. This agent generates a batch of parallel function calls. The environment returns the output or error stack trace for each, and this sequence again continues. And finally, we experiment with an agent that is closest to the standard baseline for code generation tasks. Here, the agent attempts to generate the full code for the task in one go. If the code executes without an error, it stops there. Otherwise, like previous methods, the agent is shown the error stack trace and is told to reflect on its mistake as per the stack trace. It tries again, and the process continues. So now let's see the results. Here on the x-axis, you see, or the x-axis is showing different open and closed LLMs, and y-axis is showing the task goal completion on the test normal split. Here, the score refers to the maximum score achieved by that LLM across 4 few-shot prompting methods. We see that GPT-4o struggles getting only under 50 points, even in this easiest setting, and all other LLMs are much farther behind. Next, let's see the robustness of these agents. Remember, our scenario goal completion captures whether agents can reliably complete all 3 tasks of a scenario, which are variations of each other's. We see that going from task goal completion to scenario goal completion, all scores significantly drop. For example, GPT-4o drops by 17 points, going from 49 points to 32 points. This shows that indeed agents do not complete tasks reliably. Furthermore, when we go from test normal to test challenge, we see that the main test set, which is our main test set, all scores significantly drop further. For example, GPT-4o only gets 13 points in the scenario goal completion. And when we break down the GPT-4o numbers into individual prompting methods, we find that React Agent works the best and all other methods are behind it for both the task completion score and the scenario goal completion score. We have developed AppWorld tasks in 3 levels of difficulties. This allows us to analyze how agent scores change with increasing task difficulty. Here, the histogram is showing the distribution of tasks as per the difficulty levels, and the lines show the task goal completion scores for different prompting methods. We see that the best scores drop from 55 to 20, going from level 1 to level 3, indicating agents struggle much more on harder subsets of AppWorld. And because we have written solutions for all tasks, we can also do the same for other difficulty indicators as well, like number of APIs or lines of code used in our written solutions. And here again, we see the same trend of crashing performance on task difficulty, crashing performance as the task difficulty increases. All right, so I'll address a couple of analysis questions. First, let's see how much does the score improve with interactions. Remember the example I gave at the start of the talk, motivating the need for rich and interactive coding. That example was a React trajectory with only 2 interactions with the environment. In practice, however, React, which performs the best, takes many more interactions to complete the tasks. This plot shows the distribution of tasks as per the number of such interactions. And when we look at its score at different number of interactions, we see that React does many up to 35 interactions before its score plateaus. And finally, based on manual error analysis, we find agents make various kinds of mistakes, like they make incorrect assumptions about the environment without looking into the environment. They struggle to adapt based on errors properly, and they ignore crucial pieces of instruction, use APIs incorrectly, forget state because of long trajectory, and make various kinds of coding and common sense errors. All right, so in the last few minutes I have, I want to talk about some ongoing and future work. So I'll skip this, but all right, so we want to make progress on AppWorld. So how can we make better AppWorld agents? And I think there are a number of research directions one can pursue, like learning to self-play on the AppWorld environment, training language models for interactive coding and API calls, learning a high-level skill or function library, and exploring planning-based, search-based, or memory-augmented approaches. And soon all of this research will also be doable in a multimodal version of AppWorld. So far, I have talked about agents calling APIs, but sometimes apps don't expose public APIs. So agents should be able to interact with the browser and the mobile user interface directly. In this work, we implemented many API operable apps via our own backend of APIs and databases, which can be operated with an API or HTTP client. In the follow-up work, we have also created browser and mobile user interface for all of these apps. The UI is closely similar to real apps and is backed by the same backend of APIs and databases. The key effect of doing this is that agents can operate over all modalities to solve AppWorld tasks. And since AppWorld tasks and evaluations are database state-based and process agnostic, they can be reused as is. And now I want to take a step back from what we proposed in this work and revisit this broad vision I started with to lay out some future work. We envisioned a future where AI agents get deeply embedded into our society, taking various roles and responsibilities. In such a society, agents will have to collaborate with other agents and humans to complete complex tasks. They will have to be robust to failures. They will have to be efficient with the resources. They will have to be robust to inevitable security attacks because real world resources are at play. And they will have to be socially intelligent because, after all, they will deal with people. AppWorld provides a programmatic and controllable and extensible society of people and their digital activities. This foundation can also be used for evaluation and development of agents in all of these directions. And if you're interested in any of these directions, please reach out and I would be happy to chat further. All right, so in summary, we have introduced AppWorld, which was born out of significant engineering effort by our team, writing over 100,000 lines of code. We have developed a rich and fully controllable app environment with simulated activities of people. On top of it, we developed a benchmark of complex tasks with robust and programmatic evaluation framework and showed that best LLMs struggle on it. And we discussed many future works that AppWorld can support for building better agents and new agent benchmarks. So please check out appworld.dev for Task and API Explorer, Playground, and a lot more. We have made AppWorld to be very easy to use and fast, so you can just pip install it and quickly start building and testing your agents. Yeah, and that's all I have, and happy to take questions if we have some time.
Okay, let's thank Harsh.
I take a question.
Go for it.
Thank you, Harsh, for such a great job. And I just have a quick observation about the code base. Could you please tell me what's the difference between the base DBs and the databases in each task in the trained data set?
Yeah, so base DB is kind of a common starting point for all the tasks. However, each task would have like its individual unique requirements.
Yeah.
So what we do is, imagine you have kind of like a database, and then you make a fork of it, and you make individual customizations for each task that are required to satisfy the constraints and requirements of that task.
Okay.
And that's what it is. So each task has its own database. Does that answer your question? Base DB is just like the common starting point. We populate, so this is what I was looking for. So base
So
would be kind of a common starting point, and then for each task would have on the top right, you see like a database, like a blue database. It's individual and different for each task, but the base world is common. Does that
Okay.
make sense?
Yeah, that makes sense. So the original database is not going to be modified, and each task will have its own database that can be modified by the model when it calls the APIs. And after that, you evaluate the status of the individual database to check whether it requires the state requirements. So that's how you evaluate the single job.
Yeah, so let me clarify here. So the blue database on the right is kind of the initial database specifically for that task. Now agent would make changes to it, but the point I was making, that the initial state of the database will be different for every task. To design that database, we will start with the base world, but we will make perturbations to it, or we would make some edits to it. So in this case, you see that we started with the base world. We found the appropriate supervisor, and then we made some edits to the database. Now, this is required because for this task to make sense, this person Alice has to have suggestions from her roommate on phone. So if that is not there in the initial state, the task would just not be solvable. So you have to edit the app database for that. Does that make better sense now?
Yeah, that makes sense. Thank you.
Thanks.
So this is just a quick question, but in terms of like error analysis, do you have I guess maybe like a ballpark figure for what percentage of errors came from like using, I guess came from like the explore API exploration tool, or I guess maybe misusing it or misquerying the API exploration tool.
Yeah, so we have like one experiment where we do the sublation. I'll show that. So yeah, so over here you're seeing like two numbers over here. On the left, you see like the case where agent identified the API is explored it on its own. And the second is where agent was just given like Oracle APIs. And as you can see, the improvements are not quite much. So what we can determine from this is that the complexity or hardness of the task is not coming so much from identifying the APIs, but in fact, it is coming from using it correctly and also using it in an environment, interacting with the environment, uh, handling the errors and other kinds of things. So it's less of a retrieval problem and more of a reasoning problem.
I see. Okay. That makes sense. Thank you.
Yeah.
Related to the previous question, I'm wondering if you have evaluated humans on your desk, on your benchmark.
Humans. So basically, you're asking how solvable are these tasks?
Yeah.
Essentially, that, right? So I think what I should point out is that for all the tasks, we have written solutions for all of them, and we have just programmatically verified that when you run these solutions, all the evaluation tests would pass. So if I can find the right slide, okay, so here it is. So for all tasks, we ourselves write solutions and then make sure that the evaluation passes. So this is kind of a programmatic guarantee that there is a solution for pretty much all tasks.
Yeah, but
But
when
yeah. So I think, yeah. So coming to your question now, the solutions were written by us.
Yeah.
And now you can ask this question like, okay, you can solve this task, but how likely is that a typical human would be able to solve these tasks as well? And I think uh, what a typical human is like the result would be highly dependent on it, because there's something where you need like skilled software engineers who are willing to spend a lot of time, read a lot of documentation, and do these things. And we are working on it. We don't have it right now, but what we have right now is this programmatic guarantee on based on the solutions that we have.
Yeah, I think you can do something simpler too. So instead of asking people to write responses ground up, you give them a bunch of candidates. Let's say you generate multiple distilled responses from your LLMs alongside your solution, perhaps variations of your solution, and ask people to pick the best one or rank them. That should, it's that basic humans only verify, rank preferred responses as opposed to writing them ground up. This should be a lot, even this I think should suffice for my answer.
Yeah, but how would you know how solvable are the tasks based on the preference-based outcomes?
Well, at least let's say that I go with the assumption that at least one of the solutions is good response, right? So the question is, are humans going to be able to discriminate among those candidate answers and identify which one is your solution or a good solution?
Right. I think this is, one of the cases where discrimination, I feel like would be harder, because this model generated solutions could be like hundreds of lines of code. And when you have to like compare multiple hundreds of lines of code, it could be very tricky. I mean, if I can have like a skilled programmer, they would, I think, would be much more willing to just have like a Jupyter notebook and try to solve it themselves.
Yeah,
Then
that's why I said distilled program and not just the program itself. So you can, given the thought process of your llama model, I bet you can rewrite it in a much more distilled fashion, because a lot of those thought processes just thinking and revisioning or reflecting, right? So like a lot of that I think could be distilled in a more concise statement.
Okay, got it. So you're saying take the model generated solutions and then have humans write like good solutions.
Oh, you can do that. You can do that alternatively. one can take LLM generated response or a bunch of LLM generated response, distill them into much more concise responses. So you're now comparing a bunch of concise versions of LLM responses against your solution, which is, I suppose, is very concise. I think you mentioned that it was less than
Yeah.
less than 20 lines. So at this point, if you're just comparing a bunch of code snippets that are less than 20 lines, I think this should be apples to apples comparison.
Yeah. But how would you still know that how solvable are the tasks via humans if the human can pick up my solution over model generated solution? Or
Or that I think that's a good metric to check. Or if they always pick a solution that at least leads to the correct state or the state that you consider correct.
yeah, that is a good point. Yeah, I think yeah, so I think even the solutions that we have written could go like over 100 lines of code, and
Oh,
model generated codes are even longer. So
yeah.
I think there are tricky things there. Yeah, but I think I like your session. I'll think more about this. Yeah, thanks.
Mhm. Hey, I think we have more. If we still have some time if people have questions for
Yeah.
Harsh.
Harsh, I have another question because I tried the AppWorld and I found that for some simple questions which the difficulty level is 1, the model are tend to solve the problem and mark the results as achieved or successful. But when it
Okay.
comes to like the level 2 or level 3 questions, what I found is that the model just give up, just mark
Yeah.
this as a fail, and it's not even reach the limitation of the interaction terms. For
Yeah.
example, I set the interaction terms in my code as 20 or 50, but the model just give up after like 10 attempts, 10 attempts.
Yeah.
So I just wonder how can we make this longer, make the interaction more steps that the model have the more opportunity or possibility to solve the problem with the higher difficulties.
Yeah, so I think some of it could be achieved by like just prompting and just telling it to not give up. But I think even if you do that, I'm not sure if it will be able to, solve tasks. One plot that I can show you is that which basically points to that exactly that thing. So this is the plot of on the x-axis you see the number of instructions, and on the y-axis on the right side is the score. So as you can see, there is like a huge bump on the 70. Over here, this means that there is like large number of tasks for which model is taking like 70 interactions. But however, after going from like 35 or so, there is no improvement in the score, right?
Yeah.
So what this shows is that even if you artificially force the agent to take more interactions, if the task is hard, it's just going to keep cycling and keep repeating the same thing or whatever. Basically, it's not going to succeed. So I think just that is just increasing the number of steps naively is not going to help, although you can probably do with some prompting tricks. I think it requires like other approaches to deal with the kinds of errors uh, that we are facing.
Okay, got it. Yeah. Can you just please tell me whether we can evaluate a single task after executing one single task according to the IDs? Is that possible in the code?
Yeah, it's absolutely possible.
Oh, okay.
It's just a vault dot evaluate. In fact, I might have even done it over here. So on the last line is basically that.
Okay, got
It's
it.
just dot
Thank
evaluate.
you. Solid. Thank you.
Yeah, so just ping me for any question. I was happy to help like any low level things. Yeah.
One more question. So you show the splits of your data into test and
Yeah.
train.
Yeah.
But in the evaluation, it seemed like you're only evaluating prompting based approaches.
Yeah.
Was I right that
Yeah, that's right.
was it I suppose there is no fundamental limit in terms of training, right? It's because you can't just create offline data and throw
Yeah.
it at model training.
Yeah, so basically the question is, did we train, and what is, if we did not, like, what is the purpose of this train split?
Yeah.
And the main purpose of doing the split was to do some kind of standardization, because some of the previous data sets have like released only evaluation set. And although our goal here was evaluation, we wanted to do some standardization, on what you train on, what you tune your hyperparameters on. If you want to select demonstrations, what are you allowed to use? If you want to, do like example selection based on the test example, finding like k nearest demonstration, what you should use. So all of this is for that kind of standardization. Here, the effect of doing the split is that regardless of whatever demonstrations you pick from the train set, it would never have a task which involves Amazon and Gmail. So if you evaluate on the test challenge, it would always be, those two apps would always be, held out. And people can use whatever demonstration that they can use, and they can also train in the future. And we have in fact done some training. The results were not good, so we did not include them. But I think the main reason there was that we do not have enough training data for learning this more complex tasks. What people could do is people could maybe use our 100 and these many examples, and then try to augment these with like some data augmentation tricks, and that might help.
That makes sense. Thank
Yeah.
you. My last question. Anthropic yesterday released their APIs for computer use.
Yeah.
Do you have any thoughts on that?
Yeah, so I'm like super excited about that whole direction. Now, this entire work that we have is uh, is based on calling APIs. It's not based on user interface or taking snapshots and things like that. But in the upcoming version that we have, that would be one of the modalities. So I would be very curious to see how that pans out. Now, all that said, I do feel that as a mode of operation, snapshots and clicks and all of that is just way too low level for more complex tasks. For example, if you have like a simple API call like place an Amazon order, in API space, it would be just one API call. But when you do it in terms of clicks, there will be like maybe 20 or 25 clicks, and maybe typing and things like this you would have to do. And every time you would have to have like a snapshot, right? And not just that, in our tasks, there are not only APIs, but we also have this higher level control about like coding. And when you have that, it is now much more manageable to write like this compact code and sequence of code snippets that may have like hundreds of API calls because of for loops, control structure, and things like that. Now, if you unroll all of that into like really low level like clicks and stuff, it would be just like so many clicks and so many super low level operations that I don't think models would be able to solve the tasks in that modality. Uh, so yeah, I think that there would be some challenges there. So for that reason, I'm particularly excited about this future work, where we would have these tasks where like we would have this task where lots of API calls are required, which in turn, if you convert to like UI clicks, it would be just way more. So I think it would be just super challenging for all the approaches that are out there for that work on just this snapshots and UI space. So that would help come up with new approaches. Yeah, so that's my hope.